Hello, everyone. Hope you're all doing well. Make sure we got everybody in here. Okay, great. So the test was on Sunday, Monday. I did have a couple people who didn't take it, so we're not going to go over the test today because I just want to give people the benefit of the doubt for this first round of tests and everything to make sure that they get it done. So if for some reason you didn't take the test, please email me and we can try and figure something out. Otherwise, we will be going over the test with answers on Thursday. Okay. So yeah, again, just email me if you didn't take the test for whatever reason. Your test score should automatically be up in Moodle already if you want to check it out. All right, so we're going to move into chapter 3, which is a pretty hardy chapter. There's a lot to it. So we're going to actually spend the next 2 weeks going over this chapter. We may even take a little bit more time. We'll see what happens. So I will share my screen. I do think that the guided notes are nice for this section as well. So we may hit those up a little bit along with the slides. Okay. All right, so chapter 3, hardy chapter, we're going back to mathematics. So we'll definitely be needing our calculator and our periodic chart for this one. This is on chemical reactions and reaction stoichiometry. So stoichiometry is just sort of a funky, fancy way of talking about an area of study in chemistry where we look at quantities of substances that are consumed in chemical reactions. Or we can look at a chemical reaction, and if we know how much of a reactant we have, we can figure out how much of a product we have, and vice versa. If there's a certain amount of product that we need to produce, we can figure out how much of the reactant we need. And this concept of stoichiometry is all based off of the law of conservation of mass, which we had already talked about, but this idea that in a chemical reaction, matter won't be created or destroyed. Now, when we get into nuclear chemistry, that concept will shift a little bit, but as far as this chapter is concerned, the amount of mass that you're starting with should equal the amount of mass that you're ending with. So you guys should be good now with writing chemical formulas, which are the recipes for a compound, right? So a chemical formula, we've got one down here, H2O. So that is the formula if you want to make water. You need 2 hydrogens for every 1 oxygen. Now we're going to expand on that, and we're going to start to write what are known as chemical equations. And a chemical equation is how we represent that a chemical reaction has occurred on paper. So this right here is a nice simple chemical equation. We have reactants that will always sit on the left-hand side. We have our products that will sit on the right-hand side. You can have 1 or more reactants. You can have 1 or more products. Some equations are very, very simple, like this one. Some of them can have 10, 15, 20 reactants and products. Both of your reactants and products will be separated by an arrow, and the arrow is letting you know that a reaction has occurred, or that is the step that we have transferred from reactant to product. You may also see some plus symbols. Those are going to be what separate individual materials. Okay, so in this case, we have hydrogen gas combining with oxygen gas to produce H2O. Remember, hydrogen alone is H2, oxygen alone is O2, because these guys are diatomic molecules. So when they are by themselves, they like to stick to a buddy. So we've undergone a reaction where we've started with two things where the hydrogens and the oxygens are separate from each other, and then we actually bond them together or seal them together. So when we're looking at a chemical equation, it isn't enough just to write the reactants and the products. We have to actually do something called balancing an equation. So if you look here, there are two hydrogen diatomic molecules combining with one oxygen to produce two H2O molecules. And the twos here and here are represented with that little coefficient in the front. Let's think about that. So when we're balancing an equation or we're writing an equation, we have to follow the law of conservation of mass. So the atoms that I'm starting with need to equal the number of atoms that I'm ending with, okay? So it's not just enough to say, oh, I've got carbon, and then I end up with carbon. If you've got one carbon on the left-hand side or the reactant side, you need to have one carbon on the right-hand side or the product side. Same thing, if we look at this equation here, this is the combustion of methane. So we have methane, we're combusting it with oxygen, and we get CO2 and H2O. We have to end up putting these coefficients in so that we can have the same number of each element on each side. Because you can't just have an oxygen atom disappear on you or appear out of nowhere. It has to come from somewhere. So the most important thing when it comes to balancing equations is that you don't change subscripts, okay? You only put numbers in front of your molecule, or you put a number right here as a coefficient. If there's no number written, then it's just an inferred one. You don't have to write the one. So I've got one methane has to combine with two O2 molecules, so a total of 4 oxygens there, to produce one CO2 and 2 water molecules. All right, so this is a good example of why we don't change subscripts, why we always add coefficients. So if I have a water molecule here, and for some reason, I need to have 2 oxygens, okay? I don't want to do this. I don't want to put a 2 where the oxygen is, because then what am I getting is H2O2. This is no longer the recipe for water. This is the recipe for hydrogen peroxide. This will have much different properties than water. So instead, if I need to have 2 oxygens, I'm going to do that by throwing a 2 in front of it. That 2 gets distributed to everything within the molecule. So I will have 4 hydrogens and I will have 2 oxygens. All right. We've shifted the number of hydrogens, which may or may not benefit the other numbers. So you may have to go back and rebalance some of those other things. We just don't ever want to change formulas because we don't want to drink hydrogen peroxide. Okay? We just want to have more water. So in your chemical equations, you write each of the compounds that are acting as reactants. You put in an arrow, you write your compounds that are the products. And in some cases, we also will add the phase of each of those compounds. So in this case, we're taking gaseous methane, we're combining it with gaseous oxygen, and it produces CO2 as a gas and water as a gas vapor or water vapor. So G is our gas, L is our liquid, S in parentheses is a solid, and then what we will see quite a bit, especially when we get into solutions and titration and things like that is this aqueous symbol, AQ. This just means whatever the material is being presented in a water solution, or it's dissolved in water. Hold on one second. I spilled water everywhere. Ay, ay, ay. Okay. Great. So sometimes we'll see some other symbols in there as well. One example is using this delta over the reaction arrow, which means that heat is needed in order to make the reaction happen. Okay, so if I want to get these two guys to convert into these two things, I've got to add some heat in there. Sometimes you may see like an elemental symbol over there, like a symbol for platinum or nickel. That's a catalyst that's helping to move the reaction towards the product side. So let's, the slides themselves don't actually show us how to do any balancing. So let's balance some equations. I'm gonna pull up those notes. I like those guys. Okay. So just a couple things, law of conservation of mass, right? Matter isn't created or destroyed in a chemical reaction. Here we have our reactants, here we have our products. Your states, solid, liquid, gas, and aqueous. You always want to be changing coefficients, not our subscripts. Subscripts are only for the chemical formula. And then balancing chemical equations can only balance using coefficients. Okay, so we're going to do the first two of these guys together. And then I'll have y'all work on some. So different people balance equations different ways. A couple rules of thumb that I like to use. I like to balance metals before nonmetals. If something is exists by itself, like for instance here, this one we have O2 by itself. Leave that to balance for the end, because you can put a coefficient on there and sort of fix the rest of it without changing anything. If you have polyatomic ions, as long as the polyatomic ions stay as a packet, they don't change or decompose, you can count those as like a sol or a single unit. So like in this one down here, I would say that I have one PO4 over here and I have two PO4s over here. I would just keep the PO4s grouped. Okay, so looking at this one, the way that I start off is I take inventory of what I have. So I have iron and I have oxygen. So we've got iron and we have oxygen. And then I go ahead and count up how many of each I have currently without any coefficients. Well, we're assuming there's a 1 coefficient for each. So on the left side, I have 1 iron. On the right side, I have 2 irons. On the left side, I have 2 oxygens. And on the right side, I have 3 oxygens. So I need to get the atoms on the left side to equal the number of atoms on the right side. I could start by putting a 2 here, but I already can tell, do you see how oxygen is a multiple of 3 here? And then on this side, oxygen is a multiple of 2. I have to get these into a common, this thing has to be a multiplier of 2. So I'm going to put a 2 here, which will change this to 4, and it'll change this to 6. So now I can go to my metal. If I have 4 here, real easy, I can just put a 4 right there. that changes that to 4. And then if I want to adjust this, I have 2, I need to have 6. So if I put a 3 in front of there, that will change this to 6. So now I have 4 irons on both sides, and I have 6 oxygens on both sides. So let's look at this next one, KClO3. This will decompose into KCl and O2. So KCl. Okay, so I'm going to take inventory. So I have K, I have Cl, and I have oxygen. So on the left-hand side, I'm going to count out how many Ks I have. In this case, I only have 1 K. I have 1 Cl, and I have 3 oxygens, because remember the subscript is talking about the letter in front of it. On the right-hand side, I have 1 K, I have 1 Cl, and I have 2 oxygens. So my Ks and my Cls are already currently balanced, right? They're good. So we have to look at what's happening with oxygen. Here I have 3 oxygens, here I have 2 oxygens. Again, we've met that point where we have an odd multiplier and an even multiplier. So I know that this needs to be a multiplier of 2. So I'm going to throw a 2 in front of here. That'll change this to 2. It'll change this to 2. That's okay. Sometimes you have to unbalance to rebalance. And then it'll change my number of oxygens to 6. You take whatever the subscript is and you multiply it by the coefficient. Okay, so 3 times 2 gives me a total of 6. Now I can go back and balance my other stuff. We can balance the metal first. We've got that K. So if I put a 2 in front of here, what does that do to this? It changes it to 2. My Cl also will change to 2. My oxygen is the last thing I need to balance. So I'm going to put a 3 in front of there, and that will change this to 6. So does anybody have any questions about the first 2 there as far as balancing is concerned? I mean, obviously we need to practice, right? Practice, practice, practice. But any questions on the concept of it, on what we're trying to do, what our end goal is? Okay, I want you to do the next 3 on your own. So C2H4 plus O2 gives us CO2 and H2O. Aluminum plus hydrochloric acid gives us aluminum chloride plus hydrogen gas. And then our C4H10 plus O2 gives us CO2 plus H2O. Give you about 5 minutes to work on those. Okay, so let's look at a couple of these. I'm going to go over to our board.
Can you do one of them like kind of slow? Like slow it down a bit? Is my mic on?
I can hear you, Brooke.
Oh, I'm sorry. Was someone saying something? My volume was down.
Could you do one of them a little slower? Because I
Yeah.
was struggling to keep up that fast.
Yeah.
Or maybe
Yeah.
it's just
No, definitely. We can take all the time we need. All right. So let's look at we had C2 H4 plus O2 plus, sorry, gives us CO2 plus H2O. So when you have, this is known as a combustion reaction, and we'll talk about combustion reactions a little bit more, but combustion reaction is when you have some sort of hydrocarbon combining with oxygen and it combusts to produce heat, CO2 and H2O. So you'll see this sort of happen over and over again. With these, I would always follow the rule of balancing your carbons, then your hydrogens, then your oxygens. So first we have to figure out how many we have. So I have carbon, I have hydrogen, and I have oxygen, right? There's no other elements in there. On the left-hand side, how many carbons do I have? I should have 2. Right? The 2 is talking about the number of carbons. Hydrogen on the left-hand side, I should have 4, and oxygen will be 2, the 2 coming from there. We look over at this side. For carbon, I have 1. Hydrogen, I have 2. Oxygen, I have 3. Okay, are you good with that so far, Brooke? Okay, cool. So we have a good amount of stuff on this side, so we really want to start balancing stuff on this side. So if I have 2 carbons on this side and I only have 1 carbon on this side, I have to put something in front of it to get the same amount. So the number that I would put in front of there would be a 2, because that then distributes out to the carbon and to the oxygen. So this now becomes 2. Now we have to add up our oxygens because we have a new oxygen number. So I've got 2 oxygens times 2 is 4, plus the 1 over here gives me 5. All right, leave the oxygens for the end because they're messy. And then we're going to go to hydrogen. So hydrogen, I have 4 over here and I have 2 over here. So I'm going to throw a quick 2 in front of there. If I put a 2 in front of there, the 2 hydrogens that I had are now getting multiplied by 2. That gives me 4. And then oxygen, I'm liking this because I have the 4 from here, and then I've got an additional 2 from here. That gives me 6 oxygens. Questions on that so far? On why I'm putting those numbers where I'm putting them? Okay. So the last thing we need to do, because my carbon is good, my hydrogen is good, my oxygen is not the same, right? I've got 6 here and I've got 2 here. So I'm going to put something in front of here to get this to 6. Well, 6 divided by 2 gives me 3. That will give me the 6. Questions on that one? Brooke, I'm looking at you. No. Okay, good. Let's do another one. So we've got that aluminum. We're putting aluminum in some acid. Great. So aluminum plus hydrochlor. Where is my brain today? Plus hydrochloric acid will give me a salt, Cl3, and hydrogen gas. Real quickly, looking at this, why is this combined as AlCl3? Why didn't I write that, or why didn't the writer put it as AlCl? Not correct. This is the correct way, because if you remember, aluminum has a 3+ charge, chlorine has a -1 charge. When we flip flop, we get AlCl3, and that's where that's coming from with the metal. So back to balancing, I've got aluminum, I've got hydrogen, and I've got chlorine. Those are all the atoms. I count up what's on my starting side. I've got 1 aluminum, I've got 1 hydrogen, and I've got 1 chlorine. On my product side, right now I have 1 aluminum, I have 2 hydrogens, and I have 3 chlorines. So the aluminum currently is good. Chlorine, we're at what? We've got 3, so I guess we can start by, we can put a 3 over here. That's going to change my chlorine to 3. It'll change my hydrogen to 3. So we're getting closer. If I want to get hydrogen is a multiplier of 3 here, and hydrogen over here is a diatomic, it's a 2. So I need those 2 things to multiply out. So instead of a 3, I'm going to up it by a multiple of 2, and I'm going to change this to 6. That will change this to 6. That will change this to 6. That throws me off, but I can fix it. If I go over to this side, chlorine now is 3 on this side, 6 on this side. So I can put a 3 in front of here, rather, sorry, a 2 in front of here. That will give me 2 aluminums. It will give me 6 chlorines. I have to balance out hydrogen. So I've got 6 here and I've got 2 here. I'm going to put a 3 there. That'll give me 6. And then aluminum, I can put a 2 over there to finish it up. So sometimes when you're balancing, you have to work around a couple times. You don't get it the first time, you've got to do it a few times. Let's do that next one. That's kind of a pain. So clear this out. So the next one, we've got another combustion reaction. So I've got C4H10 plus O2 is going to give me CO2 plus H2O. We have carbons, hydrogens, and oxygens. 4 carbons on this side, 10 hydrogens, and 2 oxygens. On this side, I have 1 carbon, 2 hydrogens, and 3 oxygens. 2 of them are coming from here. 1 of the oxygen is coming from here. So you total both of the compounds, oxygens. So balance carbons first. So I've got 4 here. So let's put a 4 here. That will change my oxygen to 8 plus this gives me 9. Then I need to change my hydrogens. So hydrogen, I have 10 here and I have 2 here. So I can put a 5 in front of there. That will change this to 10. It will then change this to, what do we have? 8 plus 5 is 13. Okay. So we're good everywhere but here with the oxygen. The easiest thing to do is you multiply everything by 2. So I'm going to multiply each coefficient by 2. And then I'm going to take whatever I need here and stick it in front of the oxygen. All right, so we're going to multiply this by 2. So that's now going to give me 2, 8, and 10. This is just sort of the fastest way to do these ones. So multiply it by a factor of 2 because this is a multiplier of 2. And then because I have 13 here, I need to put 13 over here. So let's count them up and make sure that it worked out. So I have 8 carbons, I have 20 hydrogens, and I should have 26 oxygens. On this side, I have 8 carbons, I have 20 hydrogens, and I have 16 plus the 10 is the 26 oxygens. So we are balanced there. Questions on that one? That one's probably like one of the trickiest ones that you'll have. So when doing those, if it's a hydrocarbon, balance your, goodbye. Okay. Balance your carbons, balance your hydrogens, see how many oxygens are left. That number of oxygens becomes the coefficient of your other oxygen, and you multiply the other ones by a factor of 2. All right, we're going to do the one with a polyatomic ion on that formula sheet. So the next one was Ag3 PO4 plus, and I'm not putting the phases in, but you know, the phases are important. I'm just not writing them right now. 3, 2 gives me AgNO3 plus Ca3PO4 2. Okay. So Ag3 PO4 plus CaNO3 end of parentheses 2 gives me AgNO3 plus Ca3PO4 2. So let's look at what we've got going on here. We've got a metal, Ag. We also have Ca. Then we have these other things, and those are the polyatomic ions. So this one here is phosphate. So I'm going to circle it here. There's a phosphate, and then here's a phosphate over here. They stay phosphates, right? PO4, PO4. We have another one too. We've got nitrate. So I've got NO3 and NO3. So because these stay intact, I'm just going to group them together when I take inventory. So they don't change, they don't become something else. Let's see what we got in the comments here. Well, the polyatomics always have parentheses. The polyatomics only have parentheses if it's multiplied by a factor of 2 or more. Okay, so do you see how this one is by itself? There's no parentheses around this NO3. It's because you only have one NO3. If I'm multiplying it by, like this is getting multiplied by a factor of 2, we put it in parentheses. This one's getting multiplied by a factor of 2 as well, so we put in parentheses. So no, they won't always be in parentheses. So you just got to start getting familiar with when you see those put together that it's a polyatomic ion. So you just recognize them. Yep. That's why for the test and things like that, if you can have a polyatomic ion sheet nearby, that'll help. And you're going to see these pop up so often, you're going to start to get used to those polyatomics. So in this case, I'm going to take inventory. I've got my metal, AG. I've also got CA. And then because these stay intact, I'm going to take them as a group, PO4 and NO3. So AG, I've got 3 here, and I've got 1 here. CA, I've got 1 here, and I've got 3 here. Oh, I like that. I like when they're opposite like that. I've got PO4, I've got 1 here and 2 here. And then I've got 1 NO3 and 2 NO3s. This is looking really good. There's going to be some sort of multiplier that gets to 6. I know that. So we can start with the metal. So if I've got 3 AGs over here, I need 3 AGs over here. So make a little bit more space for us. So if I put a 3 here, that changes my AG to 3. It changes my NO3 to 3 as well. Now I've got my so we've done the AG, CA right now. I'm going to put a 3. We've got 3 CAs here, so I'm going to put a 3 here to balance that out. So that becomes 3. And then now my NO2, I had 2. Now I've got 2 times 3, which gives me 6. Ooh, that kind of throws this off over here, doesn't it? So I had 3 on this side, and that was not quite working. I need 6. So I'm going to change this. And again, that can happen where you have to remove something. I'm going to change that, put that as a 6. So that's going to move this to a 6. My AG now moves to a 6 as well on the right side. And then we can go back to balancing the AG, the metal. What can I put on the left-hand side over here in front of my AG3PO4? If I put a 2 there, it will let me. Come on, 2 there. What does that do to the AG? 2 times the 3 gives me 6. The PO4 now becomes 2. Oh, look, balanced, 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 balanced. Equal on both sides. All right, I'm going to give you guys one to do, the polyatomic. Okay, so K2SO4 plus Ba parentheses NO3 and a parentheses 2 gives us KNO3 plus BaSO4. So you go ahead and take 2 minutes or so to work on that. Brooke, you have a question?
No.
Okay.
Thank you.
Okay, so for this guy, we've got potassium, we've got barium, we've got sulfate, and we've got nitrate. Again, just sort of getting used to these guys being polyatomics. They do stay intact, they don't break up, so I'm going to take them as a little packet. So I've got 2 potassiums, I've got 1 sulfate, I've got 1 barium, and I've got 2 nitrates. On this side, 1 potassium, 1 nitrate, 1 barium, and 1 sulfate. So actually not too bad, right? I can start with my metal up here. I'm going to throw a 2 here. That changes this to 2. It changes this to 2. Oh, and we're done. Questions on balancing? Outside of, having to just practice them. You get what the point of it is, that we're trying to get the same number of atoms on both sides. Okay, cool. If you do have questions, feel free to ask, or you can wait until the end of class and we can chat afterwards. Let's pull back the slides. Pull up the slides again. Okay, so when we're looking at chemical reactions, we do tend to see certain types of reactions come up over and over again, or we see patterns in chemical reactivity. So a couple different types of reactions that we're going to look at here: combination reactions, decomposition reactions, combustion reactions, and then also we're going to look at single displacement and double displacement reactions. So if you want to add that in, single displacement and double displacement. I'm not sure if the slides have it in there, but we will definitely want to know those. Okay, single displacement and double displacement. So when we're looking at a combination reaction, you kind of think of this in the sense of like dating. So in a combination reaction, we have 2 substances and they come together to form one product. So they start dating. So we have usually the generic formula for this is going to be A plus B gives us C. So a couple real life examples, we've got carbon in a solid form mixing with gaseous oxygen, and it produces CO2. Nitrogen plus hydrogen coming together and forming ammonia. Calcium oxide plus water to give us calcium hydroxide. So we're smooshing them together. So combination reaction predictions, metal and nonmetal. You should be able to predict the product of a combination reaction between a metal and a nonmetal, like these below. So if I am, this is just going to be in the way. If I have magnesium and I combine it with oxygen, I should be able to figure out what the product is balanced correctly, because we know metals have a positive charge, nonmetals have a negative charge, and their charges should be neutral to each other. So in this case, 2 magnesiums combined with 1 oxygen, O2, to produce MgO. Let's do this a couple times, because I feel like sometimes we kind of forget how to do that. So let's say we're going to do aluminum combines with oxygen. Okay, so we're going to write a reaction where aluminum combines with oxygen. Aluminum is a metal, oxygen is a nonmetal, so you should be able to write a product for this. So let's start first by just writing aluminum. Aluminum symbol is Al. What is the state of aluminum, solid, liquid, or gas? What's the state for most metals? It's solid. So I'm gonna put a little S there. Combines with oxygen. Now oxygen is not just gonna be O. Oxygen is one of those special diatomic molecules, so we wanna put it as O2. And I'm gonna put a little G next to it because it's a gas. So now we have to combine these two things together. Can you do that? Yes, you can. Can you name it? Yes, you can. Aluminum combined with oxygen produces something called aluminum oxide. Remember that? We name the metal and then we base and we ide it. So now if I'm going to write the correct formula for the product, we need to balance charges. Aluminum is a 3+, oxygen is a 2-, flip-flop. We should get Al2O3. So this number gets dropped here. This number gets dropped here. That's from the last chapter. Now I can go ahead and balance. Okay, I don't want to ever try and balance an equation until I've made sure each formula is written correctly. So these are all correct. So now I'm going to balance these. Just solid 2. Okay, and this is also solid. So I've got aluminum, I've got oxygen. On this side I have 1 and 2. On this side I have 2 and 3. There's that 2 and 3 again. I'm going to throw a 2 here. That makes this 6, makes this 4. And then I can throw a 4 here to make that 4, and a 3 here to make that 6. You want me to give you another one to practice on your own? Yeah. All right. I want you to combine barium and nitrogen. Okay. So I want you to do a combination reaction between barium and nitrogen.
I have a question regarding the naming of elements from last time.
Sure.
When do we change iron to like ferric or ferrous and copper to cuprous, I think?
You'll be fine calling them. You may see it as ferrous and you may see it as cupric, like on a bottle or in a name, but you'll always be fine calling it iron 2 oxide. You don't have to call it ferrous 2 oxide. But know that if you see it in like homework or something, if they're saying ferrous oxide, that's what they're talking about, iron. Okay. All right, so for this one, I'm going to write a balanced chemical equation for the combination of barium and nitrogen. So barium, Ba, it's a metal, it's solid, plus nitrogen. And again, we're going to put a 2 there because nitrogen is one of our diatomics. If we don't include this 2 here, it's going to throw the whole equation off with all of the balancing. So you need to make sure you include those 2's when you're dealing with any of the diatomics by themselves. This is a gas, so I'll put a little G. All right, so when these 2 things come together, we get barium plus nitrogen, which the name of it would be barium nitride, right? Barium, Ba with a 2+ charge, nitrogen 3- charge. So we need to flip-flop. So I get Ba 3 N 2. Take inventory, I've got Ba, I've got N, 1 here, 3 here, 2 here, and 2 here actually. So the only thing I need to change up is my barium. If I put a 3 in front of there, that now alters that. So you definitely will want to be able to do combination reactions for metals and nonmetals. It's just as simple as getting the product by balancing your charges. Any other questions with combination reactions? Now there may be combination reactions that you couldn't yourself come up with the product, but you have to be able to identify it as a combination reaction, okay? So like this one here, I wouldn't expect you to know that if you take C and O2 that you're going to produce CO2, or that if you have N2 and H2 that you're going to produce NH3. I'm not going to expect you to know that, but I want you to be able to look at this and say that's a combination reaction. 2 things getting smooshed together. All right, so if things are combining something, at some point we have to have the opposite of this or the breakup, right? Decomposition. So this is where you're in a couple, or there's a couple and then they decide to call it quits. So we have a compound C and it breaks up or decomposes into A and B. So here is a great example. We've got KClO3 for potassium chlorate, and it breaks apart into KCl and then the O2. Here we've got lead carbonate. It breaks up into lead 2 oxide and CO2. Again, just working to break those guys apart. I think those are pretty easy to identify. One thing you do need to know about decomposition reactions, metal carbonates will decompose when you heat them up. So we can see it in the formula here, or in the equation here, we've got our arrow and then the delta symbol. So anytime you have a metal mixed with carbonate, it's going to break up into calcium. Well, in this case, it'll be calcium oxide and CO2. So we expect to see carbon dioxide plus some sort of metal oxide. One of the oxygens will stay with the metal and then the other carbon and the 2 oxygens will make their own CO2. And then balancing these equations is based off of the charge of the metal. So if in this case we have Ca that has a 2+ charge, oxygen will have a 2- charge. So those balance out. So it ends up actually being just 1-to-1 for this one. Okay, the next type of reaction, which I've talked about a little bit, is a combustion reaction. So this here, we've got a propane tank and we're combusting it to produce heat. Combustion reactions are very quick reactions that produce a flame or heat. And they not always, but most often involve oxygen in the air as a reactant. So you have some sort of hydrocarbon, carbon-hydrogen mixture, carbon-hydrogen-oxygen mixture. You mix it with oxygen and you produce consistently CO2 and H2O. So when burning compounds with carbon and hydrogen in them, the products are going to be CO2 and H2O. So now you know the products of a combustion reaction. So if I was to say, what are the products of a combustion reaction, or balance this equation, you would be able to come up with the correct products because you know that if you're combusting it, you're going to get CO2 and H2O. So here we've got propane mixing with oxygen to produce, again, CO2 and H2O. We go to that previous page. In the notes, there's a couple different combustion reactions. Actually, we can sort of classify all of these. So this first one here, we've got A and B coming together to form C. So this one we would say is a combination reaction. This is a good example of a decomposition reaction. This right here, carbon and hydrogen mixing with oxygen to produce CO2 and H2O. That is our combustion reaction. This guy here, also a combustion reaction. Only thing that's different is this has 2 more carbons than this, and this has 6 more hydrogens than this one, right? So the balancing will be a little bit different. But the basic format is the same. We've got carbon-hydrogen mixture with oxygen, CO2, and produces CO2, H2O. Now the slides don't talk about what would 1, 2, 3, 4. This we'll talk about this one right now. Okay, so this is an example of a single displacement reaction. So if we scroll down on the notes here, they do. It does prompt you to know single displacement and double displacement. So in a single displacement reaction, this is like the home wrecker situation. So we've got AB plus C, and C takes A from B. Okay, so now we end up with, we had AB plus C, and now we've got AC plus lonely B. Okay, so one of the original components in the compound gets booted and replaced with something else. A double displacement is when we've got, this is like sort of our swingers situation, okay? So we've got A, B combining with C, D, and they swap partners, all right? So then we get A, D plus CB. But in this double displacement, these swingers are relatively conservative, and that the metal always goes with the non-metal, okay? So you're never gonna get the metal with the metal. You're never gonna get the non-metal with the non-metal. You're gonna get the metal and the 2 metals swapping places. So we get a metal and a non-metal and a metal and a non-metal. So single displacement, one gets booted, double displacement, they swap partners. Let's look at a couple examples of single and double displacement. Let's see if we can find some earlier up on the slides here. So when looking at these here, This one here is that homewrecker situation, right? So aluminum is looking much more appealing than the hydrogen. So chlorine ditches hydrogen and bonds with the aluminum. This down here is our double displacement. We've got a metal and a polyatomic ion, a metal and a negative polyatomic ion, and they swap polyatomic ions. So now instead of the silver being with the phosphate, the silver is with the nitrate, and then vice versa for the calcium. This one down here, also an example of a double displacement reaction, okay? The metals have swapped places, or you can say the non-metals or the polyatomic ions have swapped places. So the NO3 moves into the SO4 spot and vice versa. So you want to be able to identify those. Does that make more sense, Brittany? Single displacement, double displacement?
Yes.
Okay, great. Do we want to talk about this? Yeah, we're going to talk about this. Okay, so formula weight. This is kind of different from what we've been talking about, but formula weight is the mass that a formula has with all of its elements added together. So when you look at the periodic chart, right, let's say we're looking at sodium, the formula weight for that thing is 23.0 AMUs. If we're dealing with a compound, like let's say we're looking at H2SO4, in order to get the entire weight of this whole thing, I need to add 2 hydrogens to 1 sulfur and 4 oxygens, or you can see here 2 times the hydrogen weight plus 1 times the sulfur weight plus 4 times the oxygen weight, or 1 AMU times 2 plus 32.1 AMUs, because there's only one of those, plus 4 times the 16 AMUs. We add all of those things together, and that will give us the overall weight of the formula, which in this case is 98.1. You're going to be doing a lot of those calculations. So we'll do one together. Let's do it for barium nitride, since we're already working with that. So barium nitride, we have 3 bariums and 2 nitrogens. And I don't have a periodic chart. So barium, so to get the, so we've got Ba, 3, and 2. So if I want to figure out the mass of this entire thing, I have to take the mass of barium, which in this case is 137.327, and I need to multiply it by however many of the bariums I have. In this case, I have 3 of them. Okay. I'm going to add that to my nitrogens. So my nitrogens are 14, close enough. 14, and I have 2 of them. And so then we add those together. We should end up with a relatively large number, actually. got roughly 440. And the units on this are going to be grams per mole. Okay. Or you can say 440 AMUs. So this number times 3 plus this number times 14. So I want you to do, I'll give you one. Let's do the, let's do Fe2O3. So go ahead and on your own calculate the atomic mass, the whole atomic weight for Fe2O3. Okay, so iron, here I've got 2 of them, and the mass of it is 55 point some decimal 845. If it's like really, really close, like, you know, like oxygen is 15.999, you can go with 16. But if there's a deviation of more than 10 or a tenth, I would use those decimals, okay? We're going to add that to our oxygen. So I've got 3 oxygens and the mass on that is 16. When I plug that in, I should end up with something like 159.69 AMU. So it's not too hard to do. As long as you're given the formula, you're not making these numbers up. You're just pulling them off the periodic chart. So we'll stop there for today. We'll go over the test on Wednesday or Thursday, sorry. If you didn't take the test, please talk to me. We can figure something out. If you have any questions, stay around. Otherwise, I'd start maybe getting into the homework with this and just sort of chipping away, maybe answering just the first part of the homework questions that have to deal with what we talked about today, because this chapter is kind of dense. All right. Have a good rest of your afternoon. Bye.
Thank you.
Mm-hmm. Brooke,
Hi.
what's up, girl?
I had a question, 2 questions on the lab, and then one about something we did today.
Okay.
If
Great.
you're not.
Yeah.
So on the lab, it was, where did it go? They were just the post and the pre questions. So I just didn't understand what they were asking. One of them was identify the essential steps for filling and delivering a liquid from the pipette. But I read through like all of the introduction and like the experiments, and I couldn't find anything where it actually gave like steps for filling and delivering a liquid from a pipette.
Yeah. You can
and I
just
look it up. Doesn't
yeah, you can, and you can just use your best guesstimate
Okay.
with that, or, you know, I mean, yeah.
And then if the boiling point is recorded when the liquid enters the capillary tube after the heat is removed, Will the boiling point be recorded too high or too low? Explain.
So you measure the temperature after it's already gone into the cooling tube, the capillary tube.
Yes.
So then your boiling point will be too low
Okay.
because the capillary has already cooled some of the steam. So it's measuring the temperature at a lower value than it actually is.
Okay. Okay. I get that.
Yeah.
Thank you. And then
Okay.
I had one about sorry, I have the puppy with me today. Where did they go? On like the barium and nitrogen problem. Where were you getting like barium 3 and N2?
Okay. So
N2.
yeah, let me share the screen with you real quick, okay? Because it's just easier for me to explain things.
Sure.
Pen and paper. So where I made it up. I made all of it up. So we have barium, and we're going to combine it with nitrogen, right?
Yes.
So this is a metal and this is a non-metal. So remember that when we have metals combining with non-metals, we have to balance the charge, right? Or the overall positive charge coming from the metal has to equal the negative charge coming from the non-metal.
Yes.
So what is barium's charge always?
Oh, wait, let me look up from this one.
So
2, positive 2.
Mm-hmm.
Sorry, I don't know.
What's nitrogen's charge always?
I have negative 3.
Okay. So in order to write the correct formula for this, I take this number and that becomes the subscript here.
Oh, okay.
This number and that becomes the subscript here. So Ba3N2. Now, why do I do that? Because that's the fastest way to balance my charges. Because what is 3 times a plus 2? Plus 6. What is a 2 times a minus 3? Minus 6. When I add those together, we get 0.
Okay.
Okay?
Okay, that makes sense. Yeah.
So like if I have aluminum, which is a 3 plus, and chlorine, which is a minus, and I flip-flop, AlCl3. If I have calcium, which is a 2 plus, and I combine it with phosphorus, which is a 3 minus, flip-flop, Ca3, P2, just the way you do it.
Okay.
Okay, believe me?
Then I think I'm good for everything.
Okay, cool.
Thank you so much.
Yeah, no worries.
Have a great one.
You too. I'll see you next time.
Bye.
Lucas? Lucas, are you there? Lucas, are you there? Do you have a question, or are you just hanging out and forgot to turn off your camera and your connection? Okay, well, if you can hear me and you're trying to talk, I can't hear you. Your mic is off. So feel free to just send me an email.